In the last lecture, we saw volume of distribution of the drugs. So, take home message from the last lecture was volume of distribution is an important pharmacokinetic parameter which tells the drug's ability to remain in the plasma or to redistribute into the tissue compartments. So, the volume of distribution is high. It means the drug is leaving the plasma and it is entering into the tissue compartments. So, the volume of distribution is low. It means the drug is concentrated in the plasma and it's not moving into the tissues. We knew upon administration of the drug, it gets absorbed and then it moves into the systemic circulation from where it gets absorbed, from where it gets distributed between the intravascular and extravascular compartments. Intravascular compartment is composed of blood or plasma, whereas extravascular compartment is composed of intracellular and extracellular fluids. In each compartment, drug exists in the equilibrium between the protein bound and the free form. And over time, drugs which are in the circulation will then be metabolized and excreted from the body by the liver and kidneys. We already saw our body is made up of different compartments. For this lecture purpose, I have classified the compartments into the single compartment versus multiple compartment model. Consider upon administration of a IV bolus, drug enters into the central compartment which is composed of plasma and highly perfused organs like liver and kidneys. From there, the drug moves to the peripheral compartments where the drug perfusion is lower like adipose tissue and skeletal muscle. Some drugs display single compartment pharmacokinetics where upon administration of the drug they get instantaneously distributed to the central compartment, its plasma or the highly perfused organs. From there, the drug does not get moved to the peripheral tissues or peripheral compartment. In this, we are treating our whole body as a single compartment. So, at any point of time, if there is a decreased plasma concentration of the drug, it means the drug is eliminated from the body. Since drugs are not moving to the peripheral compartments, these drugs are said to exhibit central compartment model or single compartment model pharmacokinetics. For these type of drugs, volume of distribution is represented by a single value, which is the volume of distribution of the central compartment, which is the dose administered by concentration at any given time. Only some drugs exhibit single compartment pharmacokinetics, but many or most of the drugs exhibit multi-compartment model pharmacokinetics. In this, drugs exhibit slower distribution kinetics, which is divided into the three phases: its distribution phase, terminal elimination phase, and steady state phase. Here, the drug gets distributed between the central and the peripheral compartments. In the distribution phase, following administration of the drug, the plasma concentration of the drug declines, but the amount of drug in the body remains the same. This phenomenon will cause a single drug to have many volume of distribution values, which are each time dependent. At different times, we can have different volume of distribution of the drugs. So, in the second phase, what happens is, following the distribution phase, drugs will be eliminated from the central compartment by the kidneys or liver, causing changes both in the amount of drug and also in the plasma drug concentration. So, both gets changed here, plasma concentration of the drug and also the amount of drug in the body. So, in the terminal elimination phase, additional volume of distribution values are calculable, which are dependent on the clearance of the drug. Between the distribution phase and the terminal elimination phase, there exists a phase which is called as steady state. This is the transition point where there exists a dynamic equilibrium of a drug throughout the body. In this steady state, there is no net flux of drug between the central and peripheral compartments because the drug exists in the equilibrium. So, another value of volume of distribution can be calculated at the steady state. So, this volume of distribution which is calculated at the steady state, which is also represented as the steady state volume of distribution, which is most clinically relevant, and it is used to calculate the loading dose of the drug. Which is represented as volume of distribution in liters is equal to, this A represents the amount of the drug at time t divided by concentration of the drug, plasma concentration of the drug at that particular time t. So, the volume of distribution which is calculated from the central single compartment model, it tells whether the drug's ability to stay in the plasma or to leave the tissues, whereas the volume of distribution which is calculated at the steady state, which is used to calculate the loading dose of the drug. Compartment model is a vast topic. This is just a brief oversight between the single compartment and multi-compartment model.